we had been talking about morphisms and rational maps, and so first we had introduced rational regular functions on both quasi-affine and quasi-projective varieties, and then we were talking about rational maps first to subvarieties of a affine space, which were just so this was just to repeat it. So if say if y is a quasi-projective variety or quasi-affine, and maybe x, and y is a quasi-affine variety, maybe I just say like this. So then a rational map from phi from x to an is just given by an n-tuple of regular functions of rational functions. Kx, and so just at some points these will be regular. You can put the point p and x into it, and you go to the end. And so a morphism. So it is a rational map. So a locally closed subset y in N if there is an open subset. So I should maybe say here the domain of this rational map phi will be just intersection one n of the domains of the Fi, and maybe I will just assume for the moment that y is closed, so if y is closed, and then we have that phi is a morphism to y if the image of the domain of phi is contained in y. If it's not closed, then it must, the inverse image of y must contain an open subset in the image. So, so this is a rational map, and a morphism is phi from x to y is just a rational map which is defined everywhere. So here we have the domain of phi as a map from x to y is kind of the intersection of the domain of phi as a map to x and with the well, anyway, now it will be defined everywhere, so that's okay. So so if it's where it's defined is everywhere, and okay, so we had seen that, and now I wanted to define for you also the corresponding case for maps to projective space. It's very similar. So again, a rational map to projective space will be given by a tuple of rational functions. But you know, in projective space we have equivalence classes of points, so we have to take that into account. So let me make this definition properly. So, definition. A rational map. So again, maybe I could say that. So let X be a quasi-affine or quasi-projective variety. Rational map phi from X to Dn is given by an equivalence class F0 of Fn of rational functions, of n plus 1 tuples of rational functions so Fi in X, and the equivalence relation is that two such tuples are equivalent if you get one from the other by multiplying by the same rational function. So that X, maybe I just say right here 0 until Fn in X to the n plus 1 without 0, so this should not all be 0 function. With the equivalence relation that F0 until Fn is equivalent to h times F0 until h times Fn if for all rational functions h. Okay. So if you wish, you could say that a rational function from, I mean, if you like such abstract language, it's not particularly useful, a rational function from x to Pn is just a point in the projective space, in n-dimensional perspective space, over the function field of x. I don't think that's particularly useful, but you know, that's the definition. So we say phi equal to F0 to Fn is defined at the point P in X. Well, if there exists representatives of this equivalence class, such that at the point all of these are actually regular functions and not all of them vanish. If there exists a representative say G0 to Gn of F0 to Fn with first P lies in the intersection of all the I equal to n of the domains of these rational functions, so all the Gi are defined, and Gi of P is different from 0 for at least one I. So that means it makes sense to put P into GI, and if I now put G0 of P onto Gn of P and want to view this as a point in projective space, this is well defined. That's what's right. So if P is an element, so we say it's defined in P, and so we write that as usual the domain of phi to be the set of points P in X such that phi is defined at P. And then clearly, so this is the domain of phi, and so then phi defines a map from the domain of phi, so which allows for phi from the domain of phi to Pn, which is just P, any point P, is sent to G0 of P until Gn of P for any representative G0 to Gn which satisfies its properties. As above. Clearly, it's straightforward to see that this is well defined. If you have another representative which satisfies the same property, it's obtained from this G by multiplying all the coordinates by the same rational function, which must then also be a regular function there, so that this is well defined. So it just means at any point P, you just multiply the element in projective space, all the coordinates by the same number, and so it's the same point in projective space. So clearly this is well defined. So, and again, we don't just want to have rational maps to projective space, we also want them to subvarieties of projective space. And so, basically, we just define it as maps to projective space whose image happens to lie inside there. But you know, as we're talking about rational maps, it's a bit more complicated. So let Y in N P and your subvariety, locally closed subvariety. Then P from X.
What do you mean by locally closed subvariety?
So I'm not sure whether it was said. So it just means it's locally closed. It means it's an intersection of an open and a closed subset, and it's a variety, so it's irreducible. So it's the same as saying it's an open subset in a closed subvariety, or it's an open subset in an irreducible closed subset. Then,
But isn't that the same as quasi-projective?
yes, it's the same as a quasi. Okay, it's the same as a quasi-projective variety in Pn. Okay, if you prefer that, maybe it's just there are different words for the same thing, but maybe it's easier to always say the same. So I could say it's a quasi-projective variety. Okay, but okay, so then this is a rational map. Y, so P and Y, if phi. So I'll call it, if I take first the domain of phi as a map from X to N, and I intersect it with the inverse image. Via the actual map, which is defined. I mean, it's just the inverse image. The map is actually only defined on this thing, so I don't really have to say. This is the inverse image of Y. Say contains an open subset of X. And phi from X to Y. So a morphism in X to Y. So maybe I should say then this set is called the domain of phi. So this is now the domain of phi as a map from X to Y. So I define it to be this. So if a rational map phi from X to Y is called a morphism, again, I write this with an unbroken arrow. If with this definition here, the domain of phi is equal to the whole of X. So if I have a rational map which is defined everywhere, that's a morphism. And again, an isomorphism is a map which has an inverse, which is also morphism. So now we have defined, so from any, quasi-affine or quasi-projective variety to any quasi-affine or quasi-projective variety, we have said what a morphism is and a rational map. For the moment, we are not so interested in rational maps. It's just our way to define what a morphism is, but also rational maps are interesting. So now I can already say that a morphism somehow compares the whole of X with the whole of Y, whereas with a rational map you only kind of compare an open subset of X with an open subset of Y. So for instance, if you have a rational map which has a rational map as an inverse, it says that both X and Y contain open sets which are isomorphic. So that means they are almost, and as in the rest of the topology open subsets are very big, it means that they are almost everywhere isomorphic. So this is something which makes sense in algebraic geometry, not anywhere else, like because it's a reasonably strong notion still to say that. No, it's not so easy to find isomorphisms, so a weaker notion is useful. Obviously, if you were talking about differential manifolds, then if you want an open subset of a differential manifold to be diffeomorphic to an open set of another differential manifold, this says precisely that both have the same dimension. So that's not particularly useful. Okay, so now what do we want to see next? Okay. We can first look at some easy examples. So we can, for instance, take the map phi from P1 to P2. I claim it's actually morphism, which is given by, say, for instance, I could write as 1, x1 divided by x0, x1 squared divided by x0 squared. P1 to P2. So if I write, so these are rational functions. So this defines me a rational map from P1 to P2 because you see the quotients of homogeneous polynomials of the same degree, so that's fine. And this is a morphism because I can also write it another way. So this is a morphism because it is equal to, say, what we want, x0. So you see, I just say x0 squared divided by x1 squared, x0 divided by x1 and 1. This is the same, I just have multiplied everything by x0 squared by x1 squared. And you see that this phi, so this thing is defined everywhere where x0 is not 0. So here, this makes sense where on u0. And the second one here makes sense on u1. So together, these two cover the whole of P1. So this is actually a regular function, a morphism on the whole of P1 to P2. So we can check that the image, so what do? We send a point, so if we are over there, here for instance we set a point 1a to 1a squared, 1a squared, or if it's a point ab, it is sent to a squared, ab, b squared. So we can therefore imagine that, no, that's the same thing, no, if I multiply by, so the image therefore is, so the zero set, so I could first say, yeah, okay, this is y equal to the zero set of y0, y2 minus y1 squared, which is the set of all a0, a1, a2, such that a0, a2 is equal to a1 squared. And by what I described to you here, what we actually find is that, you know, what we see that it is somehow a set of all a squared, ab, b squared, where a, b is in P1. You can see that these two are the same. The condition is just if I multiply these two, the same as the square of this. And so you can check that the image of this map is precisely this. And this is, as you can see, a closed subset of P2, and you can easily check it's an irreducible closed subset. So we can look at the inverse map. So this is y is projective variety, and you can see the inverse morphism is just the map, say psi, which I can write as 1 y1 divided by y0 from y to 2. So in some sense we just project to the, which is, well, obviously it's the same, you know, if the coordinates on P2 are y0, y1, y2, then I can write like this, so I can write it also as y0 divided by 1 and 1. And so, in other words, we basically just project on the first two coordinates. No? The point,
So this is just a typo.
What?
Typo in the domain of psi. It should be, I think.
Domain.
Yes. I mean, in the last line, psi is from what to what? To B1. What is before the arrow?
So y.
Okay.
No? Y is the image here and it goes from y to P1. And I mean, this is, you can check that these are inverse to each other, and so we see that P1 is isomorphic to this thing. So I just write like this, isomorphic to that. Okay, let's look at some other, just another stupid example just to see. For instance, we certainly want that the identity is a morphism. So for instance, if we take the identity of Pn, in this thing, we can write this just as 1 x1 divided by x0 and so on as until xn divided by x0. This certainly is this now in this way would be defined by x0 is not equal to 0, but you can do it. You can divide by any other coordinate, and so you can also have this as x0 divided by xi, x1 divided by xi, and so on, xn divided by xi. Obviously, these are the same. And if you see like this, you see it's everywhere defined. In fact, maybe I should already say this here, although yeah, maybe I can look at this more generally. Maybe I can say that so maybe this is number 3. So more generally, so we can look at polynomial maps. Polynomial maps. Morphisms. So I had defined what polynomial maps between defined varieties, but now I want to do it for projective. So let f1 f0 so fm be some polynomials x0 to xn be homogeneous polynomials of the same degree. So let x in Pn equals projective and assume that if I take the common zero set of all of them intersected with x, this is empty. So they have no common zeros on x. So then I can define the following map. So map check x0 to fm from x to m, which just as a map is just I take an n tuple of points a0 to an, and I mean point to projective space, and I just put the coordinates into the fi. this is a morphism. Why is that? So I have to be able to express it in terms of rational functions. So, proof. As you can see, obviously, this is an example of this. And also this would be an example, because I could write this as a, in this thing, with this notation, I could write phi equal to x0 squared, x0, x1, x1 squared. Right. Now this would be the same thing. Proof. So for all I, from 0 to m, you can write f0 to fm as f0 divided by fi until fm divided by fi. The map which is defined by this is precisely the same as this. We just have divided every component here by fi of this. So wherever and this is defined on x minus the 0 set of fi. So the domain of this map will therefore be x minus the common 0 set of all fi's. That means x. So thus,
I'm just a little bit confused. In the definition, we should multiply by a rational function in all the components, right? The equivalence between...
Yeah, no, I mean, but this is not here, we don't have a rational function. So here I'm just saying, as a map, it is equal to this.
Okay.
Because what does this thing do? It sends a0 to n to f0 from a0 to n divided by fi of a0 to n and so on. But this is well defined. And so this thing we have not defined before, so it doesn't make sense to say we should multiply by a rational function. It's just that as a map, this map is equal to this map, outside this. And so therefore, and obviously, if I take on another chart, so it's also, but you see, for all where one needs this thing with the rational functions here is that if I want to look on another open subset where fj is different from 0, then I have to multiply by fi and divide by fj, and that's a rational function. Okay. So that's n is a rational function. Map from x to p m with the domain x minus the 0 set of f1, f whatever it was, m, f0 of m, which is just x, so it's a morphism. Okay, so maybe now I should go back to where was it before. So the next thing, and I want to show some properties. Next thing I want to show is that, there was something more. That's okay. So now I want to show that morphisms are indeed continuous. Let me just see, I don't want to make mistakes. So this is one of yeah, maybe I can first start by this. Just to be able to use it, what we do next, I want to say a few simple properties of regular functions. So, just the following remarks. Let x be a variety, so quasi-affine. It just means an open subset in a affine variety or quasi-projective. And let U next be open. So I think I have already said first that if I look at the regular functions on U, they form a K algebra. Oh, I told you that. So it just means you can add them and multiply them and consider, and the constant functions are always regular. And so in particular, if I have a polynomial, say f, polynomial in x1, xn is a polynomial, and g1 to gn are some regular functions on U, then it follows that I can substitute the gi into this polynomial. And I get still a regular function in U. No? Because it just means, being a K algebra means you can take polynomials in this. It's just by multiplying by constant functions, by multiplying them with each other and adding, and you stay. Another thing, so you also have that if f is an element in O of U which has no zero on U, then 1 over f also lies there. There's no zero. Then 1 over f is in O of U. And that also should be kind of obvious. Anyway, O of U was just elements in the field of rational functions. So say g divided by h, such that it is defined everywhere, so that you can, for every point, you can find a representation such that the denominator is not 0 at p. And now, if this thing has no 0, you can find such a representation so that both the denominator and the numerator are non-zero for every given point, and so you can exchange denominator and numerator and you get 1 over f. No? So you can write every p mu, you can find h representation. What is it? F is equal to g divided by h, with g and h are either in the coordinate ring on x if you're in the defined space, or in S of x homogeneous of the same degree. and with G with h of p is different from 0, and also as this has no 0, G of p is different from 0. And so I can write okay, and so that means it's also regular. No? Okay. Yes, and now I wanted to show that the composition of morphisms is a morphism. So it's a bit, obviously you want to know that. So now we have again theorem. Let x, y, and z be quasi-projective or quasi-affine varieties. By this I mean that X can be quasi-projective or quasi-affine. Independently of that, Y can be quasi-projective or quasi-affine. Independently of that, Z can be quasi-projective or quasi-affine. So we have 8 cases here. So let phi from X to Y and C from Y to Z be morphisms. Then composition C composed with phi from X to Z is also morphism. Somehow, and first as a corollary, if I have a morphism, then I can pull back regular functions. So let phi from X to Y morphism U in Y open, and okay, then phi star, we have a phi star from the regular functions on U to the regular functions on e to the minus 1 of U. So U is an open subset in Y, so this is an open subset in X. So pullback just means regular functions on U is sent to phi star F, which is just F composed with phi. So first, obviously, this is a well-defined map, and this is a K-alpha homomorphism. Well, this is kind of a trivial consequence of this, because first, we know that regular functions are the same as morphisms to A1. That we had seen, at least in the defined case, but it's always the same. No, a regular function is the same as a morphism to A1. It's just I hadn't actually told it to you in the projective case, but you know, we had seen it in the defined case. Can check in the projective case. Oh no, morphisms to A1, no, we had always seen, our definition was always about morphisms to something. And we had said a regular function from anything to A1 is the same as a regular function on any variety is the same as morphism to A1. So our definition of morphism didn't depend on the source, but only on the target. And so this is okay, so this we had seen. And now, if phi is a morphism, then if I take phi restricted to phi to the minus 1 of u, from phi to the minus 1 of u to u is a morphism. No, from the definition of a morphism, it follows that if we restrict it, then it's still a morphism. If you restrict it to an open subset, it's still a morphism, just by the definition. We just say something has to hold everywhere. So thus we just take this, we take the map from, so we have a regular function on u, which is a map from u to A1, if you compose it with this. So thus phi star f, which is just a map from phi to the minus 1 of u via phi to u, and then via f to A1 is a morphism, and therefore is a regular function. And the fact that this is a K-algebra homomorphism is trivial. No? The sum goes to the sum, the product goes to the product. This follows from the definition. And the constant function becomes constant, I mean, it stays constant. So now I want to prove the theorem. So there are a few cases. Let's just go through them a little bit. Maybe not in all detail. So first, proof of theorem. So our definition of morphism only depended on the target. So instead of 8 cases, there are actually only 4. No? Because whether y is in a finite space or projective space, and whether z is in a finite space or projective space. So let's first assume that
can't we reduce it to one case, because I think every quasi-affine variety is also quasi-projective?
Well, that we would have to prove. Because I mean, obviously,
but it lives in AN, and we can consider AN as an open subset of.
Yeah, no, that is certainly true, and we are going to do that. But for that to be legal, you have to see that this is compatible with our definitions. So, which means we have to show that with our definition, the embedding of AN into PN, just as U0, is an isomorphism onto its image. That we have to show. Maybe we could show that at first, and this would simplify things here, maybe. But I mean, now I do it this way. But I mean, at any rate, just to say it's an open subset would not be enough, because we have defined morphisms in a certain way, and it has to be compatible. No? It might be we have, two completely different definitions, and then, it's kind of... Okay. But I anyway will not make too much of a story. So first, assume, in some sense, all 4 cases are the same, so therefore it's not, assume that y is lies in AN, and z also lies in some AM. So then we can write our phi equals equal to f1 to fn, where the fi are regular functions on x, and c to g1 to gm, where the gi are regular functions on y. So in order to show that this works, we don't have to, it's enough to show the neighborhood of every point. So we have to find for every point a neighborhood, so that on this we have the composition is fine. So let y in y be a point. So in a neighborhood, say u of y in y, you can write, so just an open, there is the open subset of y which contains the point y. We can write gi equal to, say, the class of a polynomial, large gi divided by polynomial. Hi, the gi, hr are polynomials. No, and this is just a class in A of y. So this was n. Let me see, where am I? Yeah, there are m of them, but each of them, yeah, like this. And I can assume such that hi has no zero. On u for all I. No. See, originally we have that, to be, for this to be regular, it must be that I can write it in such a way that at any given point, the denominator will not be zero. But if it's not zero at a given point, it's not zero in an open neighborhood of that point, namely the thing minus the zero set of this thing. So therefore, we can assume that the denominator has no zero on u. So thus we can write, I take gi composed with phi, this is just gi of f1 to fn divided by hi of f1 to fn. This is so this is an element in O of phi to the minus 1 of is regular on phi to the minus 1 of u, because the fi are regular on x, and so they are particular regular on the inverse here. This also is regular on the same set and the denominator, but it's also not zero there. So therefore the quotient is regular on the whole thing. So this is O phi to the minus 1 of u. So let me say it again. We know that hi does not vanish on u. So on the inverse image of u, hi of f1 plus n does not vanish. So the denominator doesn't have a zero here. So on the other hand, putting regular functions to polynomial always gives you a regular function. So this is a regular function, this is a regular function. And so therefore 1 over the denominator is a regular function, and the product of these two, which is just this quotient, is a regular function. And so we get a regular function. And So, what does this say? Obviously, our map C, so on phi to the minus 1 of u, we have that C composed with phi is equal to, anyway, or whatever. So anyway, it's G composed phi G. Gm composed with phi. And so this is given by a tuple of regular functions, so it's a morphism. So on this, on this open set, it's given by this, and so altogether, so this function G composed with phi and so on is regular on this open set for every open set, but then it means it's regular everywhere. I can write it on phi to the minus 1 of u. I can write it in such a way which shows that it's open on this set, and so it follows that Gi composed with phi is regular. And so, and we have by definition, G phi composed with phi is just this. And these are, again, regular functions. So this is a morphism. Okay. Now, so if you think of it, there's the argument would be precisely the same if we allow y or z to be projective. We only have to, instead of just having n tuples, whatever of regular functions, we have n plus 1 tuples up to this equivalence. Instead of having here quotients of polynomials, we have quotients of homogeneous polynomials of the same degree, but all the other arguments are the same. So let me just do one further case, namely that both y and z lie in projective space. This is so that one can see in what sense this is. So now assume y lies in Pn. What?
Paper.
I didn't look, so it looked like some kind of demonstration of. So we assume that. So again, we do the same thing. We take a point y in y. So then in the neighborhood of y in y, we can write which one is C is equal to G0 to Gm, where the Gi are regular on U and they have no common zero on U. Okay, in principle, the idea is they shouldn't, it's defined. If you can write it for every point, you can find such a thing so that they have no common zero at that point. But then again, if you have such a point, then there's a neighborhood which contains this point. Because the condition of not lying in the zero set of something is an open condition, because a zero set of something is a closed set. Okay. And so we can write it like this. So if we, you know that a regular function can be written as a quotient of two polynomials, homogeneous of the same degree. And possibly, so at every, we can write it in such, possibly we would need for different points different such representations, but making this open set smaller, we can write it just as a quotient of two polynomials. So let me write and then explain it again. So making u smaller, if necessary, I can write gi equal to hi, or maybe large gi divided by hi, where this is the class in Sx, and the gi and hi are homogeneous polynomials of the same degree. What is it? Maybe my coordinates here are called x, so x0, maybe I call them y, y0, but maybe I call them x, x0 to xn, homogeneous of the same degree. I mean, what I mean is just for every I, these two are homogeneous of the same degree. They don't have to have all the same degree. And hi has no 0 on u. So such a gi, any such gi in OU, we can certainly write as a quotient like this, and we have to, for this to be regular on u, we must be able to find at every point a representation such that the denominator is not 0. But then, if we have this at the point, we have the neighborhood of the point, so we can replace u by an smaller open subset to have this representation. And then we have to, if we do this for every such open, if we do what we want to do for every such open subset, to be a morphism is a local property, then we are done. Okay, or to be a regular function, you know, just be a regular function means it's regular at every point. So if you have an open cover, it's regular at every point, and it's regular. So anyway, so this hi has no 0 on u. And so then we do the same thing if we take gi. So now, so let so on in a neighborhood. So let x. Let's see. Be an element in x with phi of x is equal to y. So then in the neighborhood of say w of x in x, we can write our wonderful map phi equal to f0 n, where these fi are regular functions on w, and they have no common zeros. And then we can obviously just again do the composition, gi composed with phi is just obtained by putting it into these polynomials. So then gi composed with phi is equal to gi of h0 n divided by hi h0 n on w. And so this is again a regular function on w. Is lies in OW, and the gi composed with phi have no common zeros on W, because this gi didn't have them. And so our map, C composed with phi, is just given by G0 composed with phi until Gm composed with phi. And we have seen that for every point x in x, so because x is just a point with maps to y, where y was arbitrary, so for every point x in x, we have that it's given by an m+1 tuple of regular functions, and they with no common zeros. So here's enough. Okay. So I mean, it's maybe a little bit abstract, but in some sense it's quite simple. No, we just have to follow this through. It's a bit dreary and takes a bit of time. And but there's nothing very deep going on. And now we just basically have that we can put things into polynomials and whatever. That's it. So we know the composition of morphisms are morphisms. Let me just see whether I have this. Yeah. Now I also want to see that morphisms are continuous. Obviously that's a useful thing. So we had seen that regular functions are continuous, and now we want to see that also morphisms are continuous. Where was I? Theorem. Let x and y be quasi-affine or quasi-projective varieties and then phi x to y morphism. And phi is continuous. Obviously, it is for the Göttsche topology. Now, as a the Göttsche topology is defined in terms of closed sets, we have to show that. So the more natural thing is to show that the inverse image of every closed set is closed. Because the open sets are just defined as the complements of closed sets. So that's and so, let's just do it. I mean, again, in principle, you have this stupid case distinction, but it's always the same. So we assume maybe that let first y in an so then we can write phi equal to f1 to fn, where the fi are regular functions on x. So let z in y be closed. Then we can write z equal to y intersected the zero set of some polynomials. Where, gi are some polynomials. Where were we here? In the end. And I expect you can figure out how this goes. So then phi to the minus 1 of z is equal to the zero set of g1 of f1 to fn until gn of f1 to fn. We have just put this into this. So this g1, so I just mean the zero set. Zero set means I haven't defined what this is. Obviously, it's biology. So this is defined to be the set of all. Where are we? X in X such that g1 of f1 to fn is equal to 0 until gn of f1 to fn of x is equal to 0 until gn, the same thing, f1 to fn. Or maybe I write it. If I take, can write like this, g1 of f1 of x until fn of x is equal to 0 until gn of f1 of x until fn of x is equal to 0. So that's what, it's just, these are functions. I mean, if I put this into this, I get a regular function. I can put x into it, I get some number. These numbers should all be 0. And so, as I said, gi of f1 to fn is a regular function on x, because the regular functions form a K-algebra. And so we know that regular functions are continuous, so thus continuous. And so the zero set is closed, and so this is just the intersection of the zero sets. So thus e to the minus 1 of z is just zero set of g1 of f1 fn intersected is closed in X. Okay, so no big mystery. And you can imagine, we will not do it if now y instead lies in projective space. The argument is very similar. You just have to use homogeneous polynomials instead of polynomials. So it's the same thing. So the same argument. I just say it. Works for y in here. Everything fine? You look kind of severe. Okay, so much for that. So we know that these are continuous.
Something it's not clear, I will make a noise.
Okay. And now, maybe I will kind of satisfy you to do what you asked me to do. I will show gloriously that you know, AN is indeed isomorphic to the obvious open subset of Pn. So, I mean, maybe first I should make my obvious corollary. If two varieties are isomorphic, then they are homeomorphic. So if two varieties, so for me this always means quasi-projective or quasi-affine, are isomorphic, then they are homeomorphic. Any isomorphism is a homomorphism. Now I want to show the following position. If I take the map U0 from AN to U0 in Pn, which just was the map which sends a point x1 to xn to 1 x1 to xn. So this map is an isomorphism. And this somehow justifies then a little bit more that we allow ourselves to identify AN with this open subset U0 because we see it's compatible with the structure in a strong way, namely it's really this thing which we use to identify is an isomorphism. In particular, also the topology is the same. So AN has the same topology as U0, which is the induced topology from Pn. So if you view AN as a subset of Pn, then the subset of AN is closed if and only if it's intersection of AN with a closed subset of Pn. But we'll see that in a moment. So let's first see why it's an isomorphism. That's actually not so, this kind of trivial. So if I take the map 1, so we have basically said what the map is, no? 1 x1 to xn, so where these are the coordinates. So this defines this, you know, these are regular functions I mean, these are, let me see, okay, this is not right. No. Let's see that. So we want to say to Pn. Yeah. Maybe no, that's okay. So 1 x0 to xn from AN to Pn, this is a morphism. No? Because these are these coordinates on AN, they are regular functions. No? Because 1 0 xn r and o Pn. And obviously it gives me precisely this map. No? So isomorphism. And the image is 0. And I can also say what the inverse map is. Morphism is just what is the map. If I have a point in projective space which happens to lie in U0, then I can just define the map x1 divided by x0 until xn divided by x0 from u0 to an is also a morphism. And it's an inverse map. You can see these are rational functions on Pn, and the denominator is non-zero on u0. So these are regular on the whole of u0. So xi divided by x0 are elements in O of u0, and they have no common zeros. So this then obviously is a morphism, and if you look at it, if you take a point a1 to an, first you send it to 1, a1 to an in Pn, and then you send it to a1 divided by 1 until an divided by 1. This is certainly a identity if you do the composition the other way around also. So these two maps are inverse. And this shows that indeed this is an isomorphism. And so, as you see, it's very trivial, but now, but it allows us to identify, to really make this identification. So let me just, so what I said before, let me repeat it. So in particular, if we use u0 to identify an with u0, then we get the Zariski topology on an is just the induced topology from Pn. So if x in an is closed, then it is, as it's induced topology, it means that x can be written as the intersection of an with the closure of x in Pn. Where is closure of x in P. So there's always this identification. Know that we identify the map x1 to xn with the point 1, x1 to xn, and then you can take the closure. So, and you can really think, as I said, if you want to think in a more topological terms and what one does when one wants to do nice topology, somehow the idea is that you can view, you could view x bar, so x is closed in an, but an is not compact, but Pn is compact, so we can view x bar as some kind of compactification of x. No? Obviously we use the rest of topology, all this is be taken with a grain of salt, but for all practical purposes it behaves the same way as if we were doing that. And we can also do what you said. So this I can also, if we make this indication, so with note, with this identification, x which is x bar intersected an, is an open subset of x bar, which was itself a closed subset of Pn, so it is a quasi-projective variety. So thus, if we are willing to make this identification that An is viewed as the subset of Pn, we don't ever have to distinguish between affine and projective. All varieties are quasi-projective. So I will sometimes do this when it's useful, but not all the time, just to keep you confused. And but anyway, you kind of if one wants to, so. But it is useful to be able to make this identification, and in my mind, An is an open subset of Tn. Okay, let me see, I think I don't have a natural thing to go on. Maybe I will again stop 1 minute early, and okay.